A very warm welcome to today's webinar, Build It Right the First Time EMI, EMC, and Thermal Simulation using Ansys. Thank you so much for taking your time to join us. We are delighted to have professionals, engineers, and industry experts with us for this insightful session. As electronic systems continue to become more complex, ensuring electromagnetic compatibility and effective thermal management early in the design cycle has become critical to reducing development cost, accelerating time to market, and improving product reliability. So in today's webinar, we will explore how Ansys simulation solutions can help engineers address EMI, EMC, and thermal challenges efficiently, enabling right first time product development. So during this session, we will cover key industry challenges in EMI, EMC compliance, PCB level and system level simulation workflows, electrothermal coupling concepts, thermal analysis using Icepak, heat sink optimization, airflow analysis, and integrated co-simulation workflows for accurate design validation. So before we begin, I would like to introduce our speaker for today's session. So we are pleased to have Mr. Shubhendra Mishra, who's Application Engineering HF at ARK Info Solutions Private Limited with us today. Shubhendra specializes in high-frequency electromagnetic simulation and has extensive experience in helping organizations leverage Ansys simulation for EMI, EMC analysis, signal integrity, and thermal design validation. His expertise in simulation-driven product development enables engineering teams to optimize performance, ensure compliance, and reduce design iterations. So we are confident that today's session will provide valuable insights and practical knowledge that you can apply to your own design challenges. Over to you, Shubhendra.
Yeah, thank you so much, Sita, for a warm welcome. And thanks everyone for joining. So I will just share my screen just a sec. Hello everyone. Myself Shubhen has already Sita introduced me. So basically, I deals with the electronics high frequency domain. So in this, there are multiple things here. So all the things we can't cover in just 1.5 hour webinar. So I'm just focusing today on the topics EMI EMC, and after the completing the EMI EMC, how we can optimize the thermal simulations using our Ansys tool. So as already shown about, we will start with some of the like Ansys introduction parts, how we can how Ansys is in the market right now, how Ansys is useful in the simulation phases, and what are the different products in the Ansys. Then we will move to the industry level challenges in the EMI/EMC. Then we will go with the electrothermal coupling, like how electronic simulation can be coupled with the thermal simulations. So when I talk about the Ansys, so there are multiple simulation tools in the market. But when we are talking just about Ansys, Ansys is number one in the simulation because of this global market areas. Like we have overall 6,500 full-time employees who are there to help you on each phases. The 90 plus offices worldwide. We have the proven brand here, 2.54 billion US dollars revenue in 2024. When we talk about the simulation phase, we don't much focus on the designing part. We only focus on the simulation. So this makes us different from others. And when I talk about the customer satisfaction, so approx 93% of the customers across the world are satisfied with the Ansys tools in different domains. So when like how the Ansys grows. So when we started with Ansys, there was only the fluent and mechanical structure part was there. Later, we adopted multiple physics. We go with the optimizing the Granta tools, which is for material analysis. We collaborated with Autodesk, Microsoft, Synopsys. Currently, we are part of the Synopsys. So there are the multiple other in optics field. We adopted Lumerical, Zmax, Phoenix, and when we move to other things like when in the Ansoft, we adopted where Ansoft was basically partner for the electronics, where it was basically dedicated to HFSS was basically Europe Ansoft first. Then we adopted that also, and currently we are moving with the different adoptions as well. So when I talk about the physics covered in the Ansys, so there are the different levels of the simulations we do. First is physics-based simulations, where we talk about structure analysis, like you want to the vibration or the thermal analysis. Yeah, either you want to do the stress analysis, you can do that with the structure. We have then fluids for fluid flow analysis. We have electronics for different type of electronic component, heating and EMI, EMC, anything you want to do, RF simulation you want to do, you can do that. In the semiconductors, we have different tools. When we talk about the optics field, we have optics tools also. We have a discovery where we can do the 3D designing, and the photonics applications also we cover with the physics-based simulation tools. Then above that, we have a system software simulations where like we combine multiple physics, like just in case if there is an electrical vehicle. So now we have to use different physics in one system. So for that, we have a system software simulations where we have digital twin systems, embedded safety analysis. Then again move to the systems of system. Like just for example, we have designed the vehicle and simulated all parts in the digital twin. Now I want to implement that over an environment, whole environment. Now I have to check like whether the what is the environment, like atmospheres, what are the obstacles, what are the terrains and all. So we have to optimize that also. For that also, we have a digital machine engineering tools. Then we have a simulation platform. Simulation platform helps you to go with the simulation phases. Like I'm designing one antenna in the electronics. So now I want to check that material, how like I want to optimize the time duration, like time of the simulations. I want to do the optimization phases, like I want to change some parameters and all. I optimize that. We can do that. We have a process and data management. We have a multi-physics, model-based system engineering. So these four basically deals with first we go with the physics-based simulation, then we move to the systems, software simulations, then system of system, and at last for the simulation platform, which will help you to do those. So now when I talk about the industries, so like in aerospace and defense, so basically autonomy solutions are there, which is for chip packet systems. For automotive, we have different applications like electrifications and all, energy, healthcare, high tech, and industry you talk. These are the multiple solutions which we can provide in different parts. So now that was basically a brief about what physics we are. Now itself in that physics, like when I talk about the electronics, there are multiple products in the electronics. In the structure, we have a multiple products. We have a different multiple products in the fluids and optics, machine engineering, and all. So for each type of physics, we have a different technical expert. And in case if you are interested in any of them, you can contact us and we will align a particular technical expert on that. And he will tell you that what are the capabilities of those tools. Like when I talk about the AV simulations, in AV simulation, we can do the simulation of the sensors and all. When we move to the safety analysis, there's a MEDNI, which tells you the safety regulations and all. For that type of analysis you can do. We have a connect tools where we can analyze the material or optimization phases you want to do. All those things are possible in the connect tools. Embedded tools are there, and electronics tools. In electronics itself, it is divided into two parts: low frequency and high frequency. When I talk about the low frequency, it is basically for electric machines where you want to analyze. You want to analyze electric motors, power electronics, power drains. So those comes under the low frequency tools, which is basically in this, you can see Maxwell and MotorCAD, these two tools are there for those applications. Now for high frequency, we have a different tools where HFSS, SIwave, Icepak, Q3D, EMC Plus, and NU Hertz solutions are there. So in details, I will explain you in the next slides about that. And apart from this, we have AI tools also. We have a Sim AI, we have Ansys GPT. It is basically like Chat GPT, where in case you are facing some problem, like during the simulations. So now you can ask the Ansys GPT, this is a problem, how can I resolve that? So it will give you the proper data, proper documents on that field, and you can use that. We have a digital twin. This is basically the system of system level simulations where I can import, like I'm doing some simulations where electronics structure, and fluids. All three physics are involved. So I can import all those models here and I can proceed with the simulation phases. We have an optics tool, we have a machine engineering tool. Machine engineering tools basically deals with our system of system level, where like SDK is there. SDK tells you about that when that EV vehicle is evolving, like just for example, there's a one drone. Now that drone is evolving around one area. So how in that area, how the transmission and radiations will be done for that part, those things will be analyzed through the SDK tools. SDK basically goes with the defense applications. So whoever here are from the defense applications, they can and explore SDK tools. So this was basic brief intro about all the Ansys products which I was talking about. So a basic question arises, why we need the electromagnetic simulations? So when I talk about plotting and like I'm doing a physical testing, now in that I want to plot the current, I want to plot the voltage. That is too hard to do that. So that's why what you can do is you can create a digital copy of that model, and before before going for the designing, you can import here and you can analyze anything you want. And apart from this, when you want to place the antenna over somewhere and for the exact location at exact which location I should place, and if I'm changing some of the parameters, how that will be analyzed, all those things you can do with the help of the simulations. So these are the multiple industries where electronic products are utilized. In the networking, you can see where signal integrity, power integrity applications mostly goes. In wireless, where antenna designing, antenna simulations, and antenna placement part is like mostly utilized. In industrial equipments, where EMI, EMC applications and all are most like EMIMC is the part where you in any industry you can use that. Just I'm giving you just a brief about that, nothing else. Like in the biomedical, you can see even in the biomedical applications also you can do like you have heard about SAR analysis, specific as absorption rate. That things also you can do that with the help of our Ansys electronics tools. So there is a one quote here. Electronics does not make an industry, but electronics is part of every industry. So whether I'm talking about these all the industries, so electronics is part of all these industries, though it does not make a particular industry type of things. So when I go in details about Ansys electronic tools, so starting with Maxwell, Maxwell is totally dedicated tool for electric machines and motors. You want to analyze the electric flux, magnetic flux, you want to go with analysis of power drain, you want to analyze electric motors analysis, you want to do all things you can do that with the help of a Maxwell. HFSS is a vast tool where you can go from simple antenna designing to antenna placement, and after placement how it is reacting, you can also see that. And apart from this also there are multiple things you can do that itself in the HFSS, like EMI EMC. You can do system level EMI EMC itself in the HFSS. You can do when I'm talking about the SAR analysis or RCS analysis, anything you want to do, you can do that with the help of the HFSS tool. And we have HFSS IC, which is dedicated tool for chip and chip analysis. We have an Icepak, which is dedicated tool for the thermal analysis. So now after completing your electromagnetic simulations, you will move to the thermal analysis that we call the electrothermal analysis. So to do that, first when you complete that electromagnetic simulations, you import that design here. You can proceed with the simulations. You can analyze the temperature. You can analyze the airflow. You can analyze what is the surface current density you want to plot, and like what how that fan is reacting and all heat dissipations. All things are possible itself in the Icepak. Concept EV is dedicated tool for EV industries, where you want to design a platform, any electric vehicle to connect with the system, whole system. So now how after those analysis, how you can do that, you can analyze in the concept EV. MotorCAD is there for motor analysis, where this is basically a template based tool where you can go with the analysis like you will get the inputs there and all simulations from the thermal to the all the like whatever analysis you want to do itself in the motor analysis you can do that with the motor CAD. Then we have is SIwave. SIwave is dedicated tool for PCB analysis, like from the signal integrity, power integrity, EMI, EMC, anything you want to do, you can do that with the SIwave. From the basic layout import to going with the radiated emission, conducted emission, anything you can do just for PCB level. For system level, we have HFSS. Q3D is there for RLGC parameter extractions, where you can extract those RLGC parameters to proceed with the PCB simulations. Next, we have EMC Plus. EMC Plus is directed to for where like there is some cable installed in a car. So how that cable is radiating, how that cable is affecting other components, all things are possible itself in the EMC Plus. Charge Plus is focuses on charging and discharging phenomena, where you must have heard a simulation name which is called ESD, electrostatic discharge method. So for that type of analysis, we can proceed with the charge plus. And we have CVM for RF simulations, where for there's a one data center itself in the data center, how that if some radiation is happening, how that radiation and all whole at the large scale you want to analyze, you can do that with the CVM. Sen Matrix and NU Hertz, these two tools are dedicated tool for filter designing. These are basically template based tool. These also you can that you want to design a low pass filter or high pass butterworth filter, anything you want to design. You have all you have to do is just give the input and all circuit with the model will be imported in the HFSS. You can analyze that. So across the major physics, when I talk about from the transistor level, like a nanometer to network planning base station coverage to a kilometer, all things are covered itself in the Ansys electronic tools. Like you want to do the transistor analysis, you want to do 3D RFIC, PCB, antenna elements, 5G arrays, anything you want to do, you can do that with the different like these all tools I mentioned in the previous slides. Now, when before going to the particular EMI EMC section, I will just give a brief about the HFSS SIwave both. So because these two tools are basically dedicated for the EMI EMC part. When I talk about the system level, we can do that with the HFSS, and when you talk about the PCB level, then we can do that with the SIwave. There's a one here where HFSS basically deals when I want to analyze some gain of the antenna. I want to go with the radiated emission of whole system. I want to do the circuit simulations of the whole system. So all things are we can do that with the HFSS. There's a multiple applications where we have used the media streaming devices, router, power losses. I want to analyze in the PCB for smartphones. So basically in HFSS, there is a three modules. I will explain in the next slide. Just a second. So these are the three modules which I was talking about: 3D modeler, 3D layout, and schematic. So 3D modeler is dedicated for the MCAD models, where just for example, you want to do the system level EMI simulations. So you can import model, whichever tool you are using, SolidWorks you are using, any designing tool you are using, you can import the model directly here and proceed with the simulation phases. 3D layout is for ECAD models. Like I want to analyze temperature, thermal plot, or anything of the our PCB. So first I need to import that in the 3D layout. Then we can couple that with the our Icepak tools. Or if you want to proceed with the just layout simulations, so you can do that with the 3D layout itself. Then we have a schematic. What schematic do is when I completed the electromagnetic simulations. So next step will be doing the circuit simulation of that. So for circuit simulation, we have a schematic design here where you can design any type of circuit you want. And you can just for example, there is some DC-DC converters, and there is some like LISN networks, CISPR models. So all things will be covered, and we can create a circuit for that, and we can proceed with the simulation phases. Basically, these two tools deals with the whole simulation phases. If I remove the circuit part, because circuit is a thing which we can be coupled with any of the tools. Like if I'm doing some simulation in the SIwave, I can also do the circuit simulation of the that part in the circuit schematic. Now, when I talk about the SIwave, so SIwave is a tool where not only the EMI of the PCB level, but you can also analyze how much current plot is there, how much current distribution over the PCB, voltage distribution over the PCB, or you want to do the DCIR analysis, you can do with the crosstalk, impedance mismatch, anything you want to do, you can do that with the SIwave tool. So here you can see that this is how the animations of the current plot is there and how the on the whole system, how the temperature is distributed, all things we can directly couple SIwave with the Icepak to see the temperature plots also. So now when we talk about signal integrity, because signal integrity is a main cause for the sometimes our this interference and all. So what is signal integrity? Just for example, there's a one transmitter and there's a one receiver. So there's some signal transmitting to the transmitter and receiver receiving. Now in between, what are the losses and all which these can be analyzed through the signal integrity issues. These are the major signal integrity issues: impedance mismatch, crosstalk, delay, attenuation, reflection, emissions, jitter. Process for that will be like, just for example, there's a one chip, package, PCB, and memory part. So now in the first phase, there will a write mode where you can do any type of changes you want from the driver IBIS to the receiver IBIS. When we go to the reverse action after completing here, the part, now the feedback is required. For that, driver IBIS will transmit the data to the receiver IB, but this is will be the only the read mode. You can't change any inputs or any value here. So this will be how the our signal integrity issue will be resolved. So till now, if you have any queries and questions, you can drop in the chat box. Now I will move to the EMI/EMC analysis and how we can do the EMI/EMC analysis and compliance using the Ansys electronic desktop. Different tools we can use for that. So basic question is why EMI/EMC matters today. So approx 1.8 billion annual cost is due to the EMC failures. So we wanted to reduce that cost. We wanted to reduce like approx like from the designing phase after going to the physical testings. Mostly of them faces the problem like there's a failure and again move to the designing phase. So that designing cost it increases the overall value. So for that, which is basically the annual cost for the EMC failures is approx 1.8 billions. Now, when we talk about the failure percentage of the products, so mostly when I talk about the failures, there's 40% EMC compliance failures is there on the first attempt. I'm not talking about the multiple iterations. I'm talking about the first attempt. So when the complexity increases and there's some problems, so 40% of the products, I think there might be some more, but according to my understanding, there's a 40% I have mentioned here. And when I talk about the another issue which we faced in that part due to the this designing problems, due to the first attempt failures, the average product launch day is delayed. So that also, and when talk about the cost, overall cost for the products and all that increases by the 3 times of the whatever the we are expecting. This is basically why EMI/EMC matters today, and this can be reduced with the help of the simulation phases. And how we can reduce, I will highlight you in the next slides. So different, when I talk about the modern electronics, different industries, so electric vehicles, 5G applications industries, IoT applications, AI edge computing device, and the ADAS systems, everywhere we face same problems of the EMC failures. So Now, what is EMI? So basically, the interference which is occurring due to the one, like there's some multiple devices in one environment. So now one is affecting the other. So how that is, that interfere is there. So due to that, the electromagnetic interference appears. The multiple tests here, you can see that this is the conducted EMI, the radiated EMI, the common mode EMIs. So conducted EMI, when you talk about it, is basically your near field analysis. Whatever the near field analysis is going on, whatever the issues, noises we are facing nearby the our system, which is basically called conducted EMI. The radiated EMI, it is basically the far field analysis where like some devices are placed at some distance. Now, how that are affecting also the systems we can analyze. And common mode is basically like where the both conducted and the radiated are happening at the same times. So now when we talk about the compatibility, so electromagnetic, yeah. Yeah. So electromagnetic compatibility tells you that how compatible your device is to handle that. Like just for example, I'm giving some of the power and some of the data to some device. So now how compatible our device is to immune that. Like when talk about there's a multiple compatibilities also, emissions, immunity, and there's a compatibility also. That like where both the visual disruption is occurring, where the immunity, how that system is immune to your external things and all, how we can limit unwanted energy outputs, like there are the multiple things, other multiple unwanted things are happening, unwanted noises are there. To evaluate that with the electromagnetic compatibility test. So when I talk about the electrification industry, so here you can see that there's a multiple devices, like there's a traction motors, there's a controller, there's DC-DC converters, there's a battery pack, charge port, transmissions on board, so the multiple things. So there, when there are the multiple things in one environment, so all those things can affect and can interfere with each other. So how to analyze that, how to do that whole simulations, we can proceed with the conducted and we can like do the conducted and radiated emission test, and we can perform how the nearby devices and the far devices are also affecting our whole system. So this is basically one of the examples where this is our how the real products look like when we talk about. So this is our key where you can see the car key where one of the there's a multiple things here. So here you can see that this is basically your outer structure and this is how the inner structure will look like. This is the PCB models and all the devices. So now when I import that itself in the our electronics tool. So how that analysis is done, you can analyze it from here. So that part is imported itself in the model and how the virtual prototype look likes and how the whole simulation is going to like this red zones here. You can see that these are the affecting zones where the excess of the current or excess of voltage is there. So that due to that, the whole system will fail. So now when I talk about the fundamental electronic products for the this our EMI MC parts is HFSS, where we can do that with the system level. SIwave is for your PCB level simulations, where PCB level EMI MC you want to do. Icepak is there for when you have completed the thermal electromagnetic applications, then we move to the Icepak. And next we have a Maxwell and to the data sector. So now when about the EMC failures, so EMC failures must be done with the power electronics components also. To analyze that power electronic components, first we will go with the Ansys Maxwell, then we will move to the simulation phases. So there, when I talk about according to the geometry and material complexity, so HFSS basically uses the finite element solver, where FEM solver, with the help of FEM solver, we can go with the simulation phases. Next, we have a movement of method solver, where hybrid applications like the whole system is there. So now multiple solver is required. Then we have SBR plus solver, which is basically for placement part. Now, when I'm talking about I have analyzed one PCB. I have done the PCB level EMI EMC simulation for that PCB part. Now I want to move to the system level. So for that, I need to place that PCB over the whole system. For that, we will need the SBR plus solver. Next, we have a HPC or DDM blockage solver. So in the DDM solver, there's a whole big system. So now we can't, when the complexity is too large to solve at a single time. So what we do is we divide into different parts. So like antenna array, just for example. So we divide it into multiple parts and we analyze in the one units and distribute it over all the body. So that is done with the domain decomposition solver. So as I already told you that this is basically how your physical testings will be done. So first thing will be your analysis. Then you will go to the first you will design the model. Then you go to the applications like testings. And after testing, if you face any problem, you have to again move to the designing phase. So to reduce that part, we have done the virtual compliance test where we can do according to the any models compliance, you can analyze and you can there's some CISPR compliances are there. So analyzing that, you can go with matching those results. This will reduce the cost and number of iterations also, like how much number of iterations you're performing, if that we are also eliminating. So now when I talk about the CISPR standards, so CISPR 11 is there, which is basically dedicated for the industrial equipments. CISPR 22 is there, which is dedicated for the multimedia equipments. CISPR 24 and 35 is for immunity testings. CISPR 25 is for automotive receivers, where you want to go with the receivers in the RE or C simulations you want to do. For that applications, you can do that with the CISPR 25, where 150 kilohertz, so the 2.5 gigahertz, we will operate. So basically, in most of the applications currently, according to my applications, I'm using either CISPR 25 or CISPR 15. So CISPR 32 is there for IT equipments where you want to replace the CISPR 13 or 22 with some multimedia devices. So for that, 32 is suitable. Then we talk about the electric vehicles where currently EV is in all over the markets. So to protect that from the ADAS and receivers near devices, so for that we can do that with the currently you have seen the automatic vehicles where automatically the vehicles are stopping and all. So to exactly evaluate that type of analysis in the ADAS applications, we can do the with the help of the CISPR 36. So these are the different CISPR standards. So according to these standards, all these standards have a particular limit lines also. So when I'm doing with the CISPR 25, I will put the limit line of the CISPR 25 and move with the simulation phases. If I'm doing some CISPR 11 models like for the industrial equipments or multimedia, anywhere I'm using, so I can proceed with those type of simulations. So these are the when I look for the automotive applications. So full vehicle simulation I want to do immunity, emissions, or system analysis. I can do that with the help of our SIwave and HFSS tools. When you want to do the radiations or immunity analysis or crosstalk or shielding anything, so you can do that with the SIwave. Now, if you want to go with the EFT test also, you want to go with the bus simulations or some matching the EMC standards and all. So for that also we have a component level simulations for a particular placement of now. What happens when I I have placed one antenna over a one vehicle and on the second vehicle. Here you can see that there's a one vehicle over that there's a one antenna placed, and on the second vehicle also there's antenna placed. So how that antenna is communicating with this part and how that antenna is affecting or interfering with this antenna, we can analyze that also with the help of the HFSS. Now, when I talk about the whole size, it's just for example, I'm using some mobiles or there's some, so how that the radiation coming from that device or mobile and all affecting my body and how our body is, how much emissions our body can absorb So those type of SAR analysis we can also perform with the help of the HFSS. So now when I talk about the multiple EMC tests, so first test which I'm going to explain you about that is electromagnetic susceptibility test, where we will go with the simulation phases of I will incident a plane wave on the PCB board. Now I will analyze how voltage is varying with respect to frequency at at the LED to ground phase, at the data 0 to ground, at the CPU1 to VCC to ground, and R to ground. All those things are measured here. So with the help of that, we can analyze the susceptibility test for that PCB. Now, next one is conducted emission. Here you can see that this is our basically our test setup. And in this, there are the two modes, were differential modes and common mode. So in the differential mode, current flows from the opposite directions. When I talk about the common mode, current flows in the same directions. Like you are already engineers, so these things are much more clear about that. So this is basically our test setup where LISN is there, where the EUT is connected to the LISN, and then the virtual ground and the horizontal ground. The two ground planes we have taken. So this is basically how the emission plot will evaluated in the simulation phases. So this is basically your PCB here, and above the PCB, this is your whole CISPA25 model. And this is in CISPA25 and the PCB are connected with the one cable here. So after placement, how whole system is operating, we can analyze from it here. So basic step is importing the board file, then go with the extraction part, do the system simulations, evaluate the noise, and if you're facing some problems, you don't need to again import the board file. You can directly go to the system simulation, make some changes, and evaluate again. So this is one of the case study which we have performed for one of our customer, Rockwell Automations. So in this, you can see that for the common mode and the differential mode, both we have done. So in the common mode, you can see this red part, you can see this is our measured result. And this black part you can here analyze, which is our simulation results. So how the simulation result is varying with the measured result, you can analyze it from here. And what changes we should do and analyze, so we can go with the same process for the differential mode and common mode both. Now I got the noises and all. So now how to limit that? So these are the, like, just for example, this is square A and this is square B. So for square A, there is a limit line. For that limit line, I will above that limit line, whatever the noises we are getting, that will be not included in simulation phases. So that is basically our unwanted noises which you are getting. So make some changes and evaluate again. All our target is to all the noises which are will be downside the this our limit line for whole models. So now when I talk about the edited emission test, this is basically our whole system level, like far field analysis, I will say. So you can see that for at the different levels, which is basically the result plot is here for the CISPA25 models. So differential in the differential mode, current is flowing like same process is here. And the test environment is basically like this, where one antenna, biconical antenna, or any log periodic antenna, any antenna is placed at some distance over the UT. This is basically our UT part. At some distance, this our antenna is placed. Now, how that antenna is affecting the device, we can analyze it from here. So, like I said, this is basically an anechoic chamber. One antenna is placed. There's a one UT device, and at some 3 to 10 meter distance, I can place that antenna. Now, I will evaluate how that emissions is there in the whole anechoic chamber. So, this was one of the case study for the GAMCO, which we have performed. So in this part, what we have done is for them is they have given one measurement result. We have to go with simulation phases and analyze how that measurement result is matching with the simulation results. So what they have done is they have given a one antenna which is placed at 3 meter distance from our UT or the PCB board. So to analyze that, we have gone to the simulation phases. Now you can see that I placed a little bit lower. So simulation result is matching with the measurement results. So this tells you about the accuracy of the tool also, like how accurate our tool is. So this was one of the ESD test which is done here. So in this part here, you can see that there is a one phase where PCB is not connected to the galvanic, which is basically your not grounded situations. When one PCB is connected to the galvanic metal and another two are connected to the galvanic together. So for that, that is basically a grounding situation. So in the not grounding situation, you can see that noise is disturbed. But when we move the grounding situations, so for that, noise is suppressed. So to evaluate that, we have implemented a setup here. So in this setup, there's a one ESD gun, there's a one coffee mug, which is our EUT, and there's a wooden table here, and resistors are placed out there for 470 kilo ohm. Sorry. So from the ESD, we are inserting a plane wave on the EUT and evaluating the noise. So there's a one more EMI EMC test, which is basically called conducted RF immunity test. So in this, what happens is like we are giving an RF signal to hold these four critical points. So first I evaluate that these four critical points are affecting my model. So now how voltage is varying with respect to time at these four critical points I want to analyze. I will just give a RF signal to that, and at those four critical points, you can see that how voltage is varying with respect to time. So now radiated immunity test is there. So when I was talking about the radiated emission part, so in the radiated emission part, that uh, device which was placed like an antenna which was placed was as stationary positions. So in the irradiated immunity part, that will be moving at some distance. You can see that with these two cables you can explain. So when the cable is increasing with the distance, the noises which are the voltage we are getting with respect to time will increase. So they have given at the 6 volt per meter and to a 13 megahertz frequency. We are evaluating that, and they have given the in the oscilloscope reading is this, and now we have to match at particular time for that analysis. So this was basically some of the case studies which we have performed for various customers in the previous years. So now I will just enlighten you about the workflow for the EMI part. So workflow is basically divided into two parts, where first one is your PCB level and one is your system level. So same workflow is followed for both, where first you will import the model, like if you are using Cadence Allegro, you are using LTM, you are using Zken or any tool. You can import model here in different formats like ODB++, step file, STL file, anything you want to import. You can import like for like when you're talking about the ECAD models, you can import the ODB++, EDB format, ANF, Gerber, anything you want to import, you can import it here. And then we move to the full simulations, full wave simulations and evaluate the S parameters. And after S parameter, we will move to the circuit simulations. So this is basically a multi-physics part come where one tool is getting connected with the another one. So as I, like just for example, when we are doing the 3D ECAD analysis, so in that SIwave tool will require, and after extracting the S parameter data, I will move to the circuit simulation, and after completing your circuit simulation, we will analyze your near field analysis and again move to the SIwave with proper data. You don't need to worry about the data loss when we are going from one tool to another. All the data which we are from in the SIwave will be transferred to the circuit, and whatever changes you will make here in the circuit will be evaluated from the SIwave. And you can plot the near field or far field analysis and things you want to do. So same step is for system level also. You can import the model, you can go with the MCAT translations. And again, in the HFSS, you will evaluate the S parameters, move to the circuit. And after completing the circuit simulation, you can again move to the our HFSS and evaluate the field data. So now when I talk about the physical test versus simulation part, so requirement analysis is basically 2 weeks for both. Schematic design was same like 4 weeks approx. PCB layout without any EMC check will go around the 4 weeks. Prototype fabrications, first step. you will do either, if you fail on the first step, you will debug the insights and again go to the board redesign models, retest and marginal pass, and then the certification submissions. So this is your traditional approach. Now, what you can change it from the simulation approaches, your time will be reduced from 32 to 52 weeks to the 23 to 28 weeks, which is 45% faster. So when I'm going to this part where rebuild the design models. Okay. When I'm going to the board redesign, before that, what I will do is I will just do the PCB layout plus EMI scanner, do the radiated analysis, do the iteration, the simulations, fabrication phases. Then we go to the physical EMC test. After completing this part, we will go to the physical EMC test, and there is a 90 to 98% chances like your system will pass on that test. Then move to the circuit simulations and certification submission, and your whole solution will be completed with 45% faster times. So this was basically all for EMI EMC section. So now we will move to our electrothermal analysis, which is basically for like your Icepak tool. So when I talk about the four reliability tests in electronics is basically your signal integrity, power integrity, EMI EMC, and at last is thermal integrity. So above three parts are done with the help of the SIwave and HFSS. But for this thermal integrity, we need a tool called Icepak. So what Icepak do is when we are introducing from the basic system, like basic level, we want to predict the airflow, we want to see the heat dissipation at the each points, how much overheating is there, all things we can analyze through the Icepak tool. So from like chip level to IC packages to the board assemblies to the backplane assemblies, or whole system you want to analyze. The best part about the Icepak, which makes you different from the other tools, is you can do the system level simulations, like system level thermal integrations also. You want to see the whole temperature plots, whole of the data center also, you can do that with the help of the Icepak tool. Now, you can Sweta, what is it like why thermal simulation is needed? So here there is a one PCB here. This is there's a one PCB here. So that due to the excessive current, which I already told you in the previous slides, how the excessive current are measured there. So due to the excessive current and the poor cooling, there's a one via burnout here. So to evaluate that, what we can do that we can evaluate the like import those whole model in the whole this our environment, and we can see at what particular range, what frequency, like what temperature is there. So this part you can see that it is approximately going 253 to 284, which is overheating part. So this is due to the flow starvation. Like flow starvation is basically like when the proper fluid is not reaching that particular positions. So for that, it's flow starvation. Due to that, component overheating is done. So when I talk about different versions of the Icepak, so basically Icepak has two versions where in previous we had classic Icepak also, but currently we are mostly focusing on the ADT one. So in the ADT Icepak, we are focusing state analysis. You want to like, this is basically in your ADT workbench, where ADT is basically like where your all the other tools are there. It is a workbench for electronics. So where you can do all this analysis. When I want to couple that Icepak for PCB level, like I am doing some signal integrity, power integrity analysis in the SIwave. Now I want to couple that model directly to the SIwave. So I can directly couple that PCB with the Icepak in itself in the SIwave. So this integration there will be no data loss. Just for example, I have performed some DCI analysis. I've evaluated the current, the voltage and all. Now I want to plot the temperature on the whole body and see how that, like in case there's some excessive current over some part. So now how due to that excessive current, what is the temperature at exactly that point, we can evaluate from the Icepak in the SIP. So when I talk about the ADT Icepak, this is basically a model where I can couple HFSS with the Icepak. for your simulation phases. Like there is a one waveguide here, or where there's a one waveguide, there's a one patch part. So all things we can evaluate from this part. We can by coupling it with the, and for power electronics also, like I'm doing some coil analysis. So for that also, I want to couple the Maxwell tool with the Icepak. I can do that also. I can couple Q3D with the Icepak. So Icepak is a tool which can be coupled with any of the environments. So here you can see that these are the ADD workbench tools: HFSS, Q3D, circuit, Icepak. So mechanical analysis, electromechanical analysis you want to do, if you want to do the simpler analysis. So all those tools are there. So I can couple any tool with the Icepak and proceed with the simulation phases. So basic what inputs we require. So for different applications, I have to assign proper boundary conditions to our model. So for that boundary conditions, I will say like assigning the thermal. So blocks, there are different boundary conditions here. Blocks which will be assigned for the power dissipation. Like I want to go give the power, apply the power dissipation in the whole volume. So for that, I will assign thermal block thermal boundary conditions. Grills are for permitted vents, like there's some vents models there. So for that, I will assign the grills. Openings is for allow the airflow. When I want to analyze the airflow analysis, I am just designing a test. For example, I am implementing the fan in the model. So how that fan is giving the airflow analysis, we will first assign the opening boundary conditions on that part and again move to the submission phases. Plates are there where the like I don't need to worry about the meshing. So for that very thin objects, we will apply the plates. Resistance is for calibrated thermal models. Sources are where I want to like, here you can see that when I was assigning the power distribution in the volume, I was given blocks, but for the 2D surfaces, we will give the sources. Walls are basically for thermal boundary conditions on the 2D surfaces. Like I want to evaluate uh, our whole radiations and all in one system. For that, I will assign a wall. EM losses is when I'm coupling that one tool with the another tool. Like I'm coupling our HFSS with the Icepak, I'm coupling a Maxwell with the Icepak. So whatever the EM data is there to evaluate, to take that EM data in the simulation phases, we can assign the EM losses here. And how to apply that? Just click on the assign thermal and all things will appear here and you can assign any of these. So now when I talk about the meshing, so in meshing, basically in Icepak, meshing is very easy. All you need to do is just go to the global mesh settings, click on that. Then there's a one slider will appear here. And with the help of this slider, there are multiple courses like coarse, resolution, and fine. So when I talk about the coarse, medium, fine. So according to that, your mesh counts will be evaluated. So 126 cells for the very coarse. For the coarse, there will be 23 cells. And medium, going with the medium analysis, this is basically our resolution sections. Now the fine mesh we want to generate or very fine mesh you want to generate, you can see it how those will look like also. So just by clicking on the global mesh settings, you can go with the automatic. This is basically automatic applications where you can directly slide and see how the meshing will be generated. So these are the basically unsolved geometries, these two for the very coarse and the coarse part. This is the extremely fine mesh we have generated. And this is sufficient mesh resolution part, which was I was talking about in the medium phases. So mesh regions I want to define first, like this is one of a model. Now I have to define particular mesh regions and what part I want to like give that meshing part. So without any mesh regions, you can see that this is basically heatsink and packages. So evaluate that there's a no mesh region. So 1.5 million cells are generated. So when the particular fine mesh is created, like with the help of the box, we have created a box here. Now I have given the mesh region. And after creating the mesh regions, I evaluated how the meshing part is there. So here you can see the 126K cells are generated here. So this is your coarse outer mesh, and this is your fine mesh around the heat sinks. So above, like apart from this part, all the simulation phases have applied the course mesh, and in this part, the particular heatsink part, we have given the fine mesh around the heatsink. So these things are also possible, and you can do with the proceed with the simulation phases. So when I talk about the mesh results, so directly you can click on like your model, select the bodies where you want to give. Like in the previous slide here, you can see that this was your body. So now for choosing the first the body, then right click on that body, assign mesh regions, and choose which type of mesh you want to exactly give on that mesh region. And then one mesh region will be created, and you can arrange according to your applications. You can create a, like you can move it from some bit distance, and you can generate any models, and according to that you can give the mesh priority also. Just for example, I have given the multiple mesh regions. So accordingly I can directly give, like there are multiple there's a cold plate, there's a mold, there's a cable, there's a CAD geometry. So accordingly I can assign the mesh priority, and mesh priority will tell you like which mesh will be solved first and which will be later. So how the mesh priority works, like first I validate the model, then you will see there is some issue. Like just for example, this fluid volume and the cold plate are intersecting. So in that phase, what I will do is I will give the intersecting bodies a self, like our priority. So first that cold plate will be analyzed, then the fluid volume will be analyzed, and by this phases, this your intersection part will be reduced. Then again evaluate, and your result will be like this will become under the your warning zone, not as an error. And you will do the object priority section. After that, you can visualize the mesh. Just click on the mesh viewer, and accordingly you can change whatever results you want to, like you want to see the surface on the mesh on the surface, you want to see on the particular volume, or you want to see on the particular object or the boundary selections where you have given. You can see all those type of meshes in itself in our Icepak. So by default, by raw surface only mesh, and the surface of only is off, and the color by object off. Like the object color will be deselected, and you can evaluate that. And after completing, like after generating the mesh, you can now, like that was a basically automatic method. Now, if you want to go with the geometry applications also, like on the particular geometry, particular body you want to plot the mesh, you can do that also. Now, when I talk about the PCB, like I just, for example, I want to import a PCB in the model and evaluate how that simulation will work. For that also, I can directly create the PCB from this section and proceed with the simulation phases. First, I need to import the PCB model, and that will be I will import the PCB model, and after importing the PCB model, I can directly couple it with the model. So how to import that PCB model? I will just click on the file section, and when I will import that, there are the multiple courses for that PCB. Now, for that was for the whole system. For the particular PCB also, we can generate the particular mesh. So when I want to analyze, like I already told about the HPC analysis. So in case if you have HPC license, you can go with the reducing the simulation time and going with the particular monitor points you can analyze at each phases. So this is basically for the which I was talking about the SIwave Icepak model. So in this, you can see that this is basically your Icepak GUI, where you can import the files, you can view, you can go with simulation phases, you can do the crosstalk analysis, you can do any type of analysis you want to do. When I talk about thermal analysis, first you need to do the DCIR, and after completing the DCIR, when the current and voltage plot is ready, you can directly export that with the Icepak, and you can proceed with the thermal simulations. So here the thermal part is evaluated. It's the PCB models and how the temperature is distributed all over the PCB. So these are the multiple simulation which we have performed for the our this Icepak. So there's a one heat sink fan assembly. There's a one thermal conductivity over the whole PCB modules. There's a one this- so here the temperature contours are plotted. So for the data center, for the drone applications, for each applications we have performed the Icepak simulations. So when I talk about data loss, like when I'm moving from one tool, just for example, I'm completing the whole simulation in the SIwave, again moving to the Icepak, then again moving to the SIwave for evaluating how the current and voltage are again for that phase. So this is basically your electrothermal physics, where electromagnetic data you will analyze, you will export that power loss into the Icepak, and after completing the Icepak, you will import that temperature again to the HFSS or SIwave tool, and you can evaluate how the convergence is there, how the results are changing and all. So for that analysis, you can go with the electrothermal analysis. Now, when I talk about multiphysics. So this is not like I just told you about the one coupling one tool with another. You can couple all other tools. Like I'm just, for example, I'm performing some electrical simulation in the HFSS or SIwave. Now again moving to that, I will just do the simulation in the Icepak. Then I will do the stress or vibration analysis I want to do, shock analysis I want to do. I will do that in the mechanical. And after completing this phase, I will move to the Sherlock for the reliability analysis. So in mechanical, in structure, there's a one tool called Sherlock, which deals with the lifespan of the body, like each component, how much reliable each component is. So for that type of analysis, you can do that with the Sherlock. So this is basically the workflow for whole our multiphysics. And as I already told you that Icepak is a tool which we can couple with any of the tools, other tools, either in the HFSS or Maxwell or Q3D or SIwave or mechanical or going with the Radoc and all. You can do that, all those things here. So multiple physics can be combined with for the PCB designs. Like I'm doing the PCB design. So for after designing, you have to move to the electrical simulations, then do the thermal, then do the structure, and couple it with each other. So that's all from my side. This is basically my mail ID. You can see it from here. And if you have any queries or you want to explore the tools, you can directly contact me over this mail ID and I will guide you on that.